In this video, we're going to be looking at exponential, decay, and growth. So first things first, what do we know about exponential graph? We know them that they come in the form y is equals to your a to the exponent x. So if we're looking at a graph for this one, we would know we can only have a graph where we have your a being greater than 1, because you can't have a graph for y is equals to your 0 to the exponent x. And how does that graph actually look? So the graph for that one would actually look like exactly when you are making profit within your company. So you're going to be having a graph that goes like that. So now let's just say, for instance, where you are having a graph that is representing a decay, that one is for your growth. Your exponential graph that is showing your signs of decay would be like a mirror graph of this one, but it's just going to be going in the other direction. So this would be when you're having a graph that is less than that one. So now let's put it into context with regards to this type of examples that you're going to have. So suppose your p is equals to your f of t, or p is your function of time. So p is an exponent function of t with base a greater than 0. Then if p is equals to your f of t, then we'll say we have p of 0, then we have a to the exponent t. So these ones, you don't have to worry about this one. I'm just basically trying to explain some of the terms. So this one will always be your initial value that you're going to have. Then this one would be your decay or your growth factor. Then this one will be given in time. So as we know, the decay or growth factor can be written as your a is equals to 1 plus r, or it can be written as a is equals to your 1 minus r. In this one, this would be your growth. Then in this one, this would be your decay. So at the same time, I'm just going to try and show you an example of how you see your case 1 and your case 2. So for this one, I will just call it case 1. Then this one, it's case 2. In here we have our a being greater than 0, and in here we have our a being less than 0. Then we will know that means we are having a decay function. So if I'm given a function, suppose I'm given 2 functions in case 1 and case 2, I want you to notice something which is important that they also like to ask. We have f of t, then we can just come up with any initial value. So let's just say we have 10. Then internally we will say we have how much? We have 1 point, I think I can even say 0.82. You see? So now for the second one here, I'm gonna say I have my function of time is equals to 10, but internally what do I have? I have 0.84. So you are having something like this. Remember, here you're supposed to write your t, here you're supposed to write your t. So here's one thing that you have to note always. You see here I've written that I have my a being greater than 0. Here I've said I have my a being less than 1. So each and every time you check this type of question, so if you are given a function like this and they ask you, is this a type of a function that shows exponential growth or exponential decay, you can only determine it by checking the value of your a. If you check and see that your value of a is greater than 0 or it's greater than 1, this means it's your exponential growth. But if you check on this one and you see that within your function you are having your a being less than 1, that means that would be your exponential decay. So now let's just say for case 1 they ask you something like, also this is one of the questions that I know they like to ask, within this function what would be your exponential growth rate. So if they ask you to find the exponential growth rate for that one, you will write, you have your a is equals to your 1 plus your r. So now you start with the value that you have internally. What is that value? Your a, it's your 1.082 equals to 1 plus your r. We're working the rate, which is in percentages. So now you will say your r is equals to your 1.082 minus 1. Then your r will be 0.082. But remember, it has to be in percentages. So we're going to multiply this by 100. Then it will mean your r would be your 8.2 percentage. So if you are going to conclude, it will mean the growth rate factor for this function is 8.2%. So that's also one of the questions they ask. Then if we come to this part, you're still going to be following the same step, but now you are in case 2. You're not going to be using a is equals to 1 plus r, because of what? You've noticed that your a here it's less than 1. So it means now you have to use the formula, your a is equals to your 1 minus r. Your a is your 0.84, then you have your 1 minus your r. Then you'll take your r to this side, then you'll have your 1, you take this one to the other side, minus your 0.84. Then you multiply, whatever answer you get, you multiply by your 100. Then you will say your rate for decaying at this number that you're going to get. So I just hope that actually makes sense when it comes to the rate questions. So now we're going to continue and focus on this one. So those were just some of the basics that you had to understand before we look into these types of examples. I have to find my other thing because this red. So I have to use this one. Use this one. So yeah, now we're going to focus on this one. They're saying aspirant decays at a rate of 20%. So I'm going to highlight the keywords. You have decays. We're going to be working with exponential decay. They've given you the percentage there per hour. How much aspirin remains in your blood after 1 day, after taking 500 milligram of aspirin. So here we're working in quantities. So now I can just say, let quantity be a function of time with t in hours. So since we are working with quantities, I can just say, let quantity be a function of time with time t in hours. So now we're about to start. So now we can say we have q is equals to your q0, then you have your a to the exponent t. So the other example, I was just using a p, but you'll always change with respect to whatever you are given in the example. Here I'm calculating my quantities, so that's why I'm using my q's. So now the q0, remember I said this one, that's our initial quantity. And you can see here we are given an initial quantity, and I said, now we said let the quantity be a function of time with time t in hours. Here, what did they give us? They gave us per hour, but they want us to find the aspirin that remains in the blood after 1 day. So hours in terms of a day, we know this one we're going to be using 24 hours because a day has 24 hours. So how are we going to start with that one? Since we are working with an exponential decay, we are going to be using that case 2. Our case 2, we said we have a is equals to 1 minus r. You see, we have that 1 minus r. Then sorry about that, my phone was ringing. So as I was saying, since we have an example that shows it's decaying, we're going to use 1 minus r. But if it was showing an aspirin was growing at a rate of 20%, we're going to be using that case 1, which is a is equals to 1 plus r. But in this, it's decreasing. So we're going to see, what do we have? They've given us the rate. The rate, remember, here it's 20%. We just have to take this 20% and divide it by 100, because you can't, it's going to be difficult if you're working 1 minus 20%. It's just best to just divide it with 100. So you will have your a is equals to 1 minus your 0.20. Then what would be your new a? You would have your new a of 0.08. So if you have your 0.8 and we have our initial quantity, so it means now we can just say we have q is equals to this initial one, we have 500, then our a is 0.18, then this would be to the exponent t. So now we can come and say we have this 500 into 0.80 to the exponent t. As I said, they said the aspirant decrease at a rate of 20% per hour, but now they want you to find what amount remains after 1 day. And I said a day has 24 hours. So here you're going to put 24. So now you work out your final answer. You would find out that it's going to be approximately around 2.36 milligram, but you're going to write it in full. So now after this one, you do your conclusion. The most important thing in calculus always do your conclusion. You're going to say after 1 day 2.36 milligram that's gonna remain in the blood. So that would be basically where you do your final conclusion. You do your calculations, show all your working out, then you do your conclusion. So I think we can also do one more example. So yeah, we have another example which reads like this. If a quantity decreases at a rate of 10% per hour, what percent remains after 3 hours? So with this one, we're still working in quantities, so I can just say let quantity be a function of time. Then we'll say with time in T hours. So how would that look like? Then you'll say you have your Q is equals to your QO, you have your 8, the exponent T. But in this example, you will notice we don't have an initial quantity. What do we have? We have Q is equals to QO. Then remember, they are saying in this example that a quantity decreases at a rate decreases. It means now we have a decay. So when we are working out our A, we're going to be using the case where we have A is equals to 1 minus R. We'll say our A would be equals to 1 minus the 0.10. We're just dividing this by 100. Then your A would be equals to your 0.9. Then we can just say we have that 0.9 or 90. Then we have it to the exponent T. Then we have Q is equals to Q0. We have 0.19. Then we have to check the time. They say if a quantity decreases at a rate of 10% per hour, what percentage remains after 3 hours? Then you input your 3. Then you can say you have your Q is equals to your QO into, I think this one would give you something like your 0.729. Your 0.729. So which basically you just take this value and multiply it by your 100. Then I think, yeah, it will give you something like 72.9%. But since I don't have a calculator, you will confirm on your side. So in other words, the quantity decreases at 90% each hour. Basically meaning you keep 90% each hour and you are having 3 hours. In another form that I would write it is if you're having 3 hours, it's just simple to write. You have your 0.90 by 0.90 by 0.90. Then this is going to give you how much? This is going to give you your 0.729. But for the sake of calculus and the steps, you might have to write it in this way and make your conclusion here. But if it is something that is in multiple choice, you can adopt this method of solving, which is also fun. But for the longer format, try to explain it in this way or write in this way. Then write your nice conclusion at the bottom. And that's it with this exponential questions. So I guess I'll see you in the next video.